And we're back for probably the last one on Twisted Pair. We just left off talking about impedance of our cabling. And again, I don't need you to know these formulas, but just trying to remind you that as I increase the frequencies, it throws all of this math off. And the only way it can be rebalanced is changing the structure of the cable. Because again, we need to come up with 100 ohms impedance every time. So the structure of the cable has to be adjusted to get the impedance back to 100 ohms. So therefore, over the years, the categories of cable have been created to do that. That's kind of the easy way to think of that. So if I take a look, categories basically 1 and 2, if you will, was your typical old phone cable, analog phone signals. Color coded, but not paired or twisted or anything. So able to handle very low amounts of data, in the dial-up modem kind of days. Handful of maybe up to like a meg kind of thing. Not much more than that. As we move into category 3, we start getting the wires paired up and maybe lightly twisted. Here's 4 wire and here's an 8 wire, able to handle 10 megabit. I kind of excluded category 4 because that was mainly for like token ring. So I jump over to category 5, category 5E. This is relatively recent. Many networks are probably still even using this because this was able to support 100 megabit, even a gigabit. Category 5E able up to a gigabit. You'll notice now the wires are paired and distinctly twisted, much more tightly, if you will, to handle the more bandwidth that we're going through, the higher frequency to give us more bandwidth. This is your category 5, category 5E. As we move into 6 and 6A, which is probably what newer networks are putting in right now, or the future of upgrade for folks that are looking to upgrade in a few years. Category 6 able to handle 10 gigabit, and one of the reasons it is what's now happening with category 6 is there is a plastic divider here in the middle that, if I look at it this way from the end, it's kind of like a plastic plus sign. That is a insulator to keep your 4 wire pairs separated. It's trying to reduce the amount of interference between the wire pairs. So the wires are twisted even tighter, more of a twist pitch, and I'm keeping the wire pairs separated so I don't have any kind of coupling or anything weird going on. Again, as I'm increasing the frequency to get my higher bandwidth up to 10 gig. As we move ahead in the future, we're getting into category 7, category 7A. What you start running into in many cases is category 7 looks roughly like this, category 7A looks roughly like this. What you're running into now is each wire pair is insulated, and there's typically a foil shield or a braid around the whole, all 4 wire pairs. And this is able to handle 10 gig, and even they're looking at 40 gig, 60 gig stuff going on right now for this, and handling the capability, or I should say, figuring out the capability or the capacity of this. So we're into the on our way to 100 gig, but not there yet with category 7, category 7A. So if you take a super quick examine now, over the years, not twisted, lightly twisted, twisted more, twisted, separated, shielded, and the whole cable shielded. The structure is changing over the years to be able to accommodate the higher frequency, but keep that impedance down to 100 ohms. And that is kind of the deal with the impedance and the wire twist in the categories, kind of all wrapped up in one for you. As we move on to next characteristic of twisted pairs, termination, I'm just going to highlight this real quick. We are going to do termination of our patch cables in chapter 910, if you will, chapter 9. But we'll just give you a quick heads up. Our twisted pair, our patch cables, typically terminate RJ45. We're going to use our 568A or 568B color code. Again, you will eventually need to know these. Usually what happens is after you terminate a couple, it starts sticking in your brain. But here's your 2 color codes. Your A color code with white, green, green, white, orange, blue, white, blue, orange, white, brown, brown. And I mentioned this before, I'll mention it again. It looks weird, but this is from the days of phone, where the blue wire pair here in the middle was like line 1. The orange wire pair around it was line 2. That also tells you that if you were to plug a traditional phone cable into an RJ45 outlet jack, it does work. And your data cabling, if you wire up your building using data cabling, data jacks in every office, you could use one of these for a phone line. It could be used. That's why this standard is laid out the way it is. It looks weird, but it works for that purpose. And then here's your 568B color code: white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. Again, eventually you'll need to know them. If I'm terminating a straight through patch cable, I'm going to terminate both ends the same. I'll use 568A on patch cable N1, and I'll use 568A on patch cable N2, and that would give me a straight through patch cable. If I needed to make a crossover, I'm going to cross all wire pairs. I will flip-flop the oranges and the greens, and I'll flip-flop the blues and the browns. That would give me a gigabit crossover. And that's going to flip-flop all the sends and receives, so I can connect two similar devices together. A switch to a switch, if you will. A couple of the things that you run into with twisted pair is some electrical characteristics, some terms and things that come up. One of the first things they mention is propagation delay. Propagation delay is the time it takes for a signal to travel from one end of a twisted pair cable to the other end, if you will, 100-meter length of cable. This is actually handy to know because there is actually a known factor. When you go through a certain gauge of wire and certain distance, it takes so many nanoseconds. Well, that's actually handy to know. If I know it takes so many nanoseconds to go through 100 meters of cable, I can now use a meter called a TDR, time domain reflectometer. I can use a special meter, a TDR meter, and I can now hook it into a cable, send a pulse down. When it hits the other end and bounces back, I can time that, and if I time it, then I can use some math and say, well, it took me so many nanoseconds, so this cable has to be 63 meters long. That's actually very handy. So when you start talking electrical characteristics, propagation delay is very handy to know how long it takes to travel a certain length of cable, and then my meters sometimes take advantage of that to help me measure length of cable. And again, when we get to troubleshooting, we'll explain this more, but just give you a quick heads up. If I know a cable run is 73 meters, and I hook a TDR to it, I hook a meter on that's able to measure distance, I hook it up and it comes up 43 meters, I know I have a cut or a break in the cable, and I know approximately where it is. So it's very valuable, very handy piece of information, and it's also very useful in our meters. Another electrical characteristic I run into is something called delay skew. Delay skew is the difference in propagation between pairs in a cable. Again, when I have 4 wire pairs, if this is too large between wire pairs, it can be a problem. And here's a graphic trying to show you delay skew. Delay skew is just okay. Delay skew is this: if I send a signal down a cable, all these bits should be arriving at the other end at the same time. But if my wire pairs are terminated oddly, which we'll get to in a second, it's possible to have some bits arrive on the brown pair and a fraction of a second later arrive on the orange pair, a fraction of a second later green pair, a fraction of a second later blue pair. Well, that's not acceptable. You start getting jitter. You start getting bits out of alignment. And one thing that can cause that, if I look at the picture on the right, if I do a sloppy termination into my patch panel, I'm picking on some poor person that had this picture online. I just grabbed it offline. If I look at these brown wires over here, they're terminated nice and tight. And then I look at the brown wires way over here, they're longer. So if I start sending a chunk of data down this cable, these bits will arrive here, and a fraction of a second later, the bits coming down the blue pair arrive here. I'm going to get a little bit of delay skew out of this. And that gives me this difference in propagation delay between pairs, because technically this blue pair is longer than the brown pair when I look at the whole length of the cable. Delay skew can be caused by just that, a sloppy termination. What piece of equipment can observe these disturbances? Hey, look at that, TDR, time domain reflectometer. This will actually show the disturbances in the cable. I have to resist the urge to say disturbances in the force. This will show the disturbance in the cable. When I do a normal cable map on this, I would see a flat graph here. So if I do a cable scan, I normally see a flat graph. When I start seeing large bumps, I know there's issues. We'll get to some details of this when we troubleshoot, but just to give you a quick heads up, if I am using a TDR to measure length of a cable, and I kind of grabbed this offline, this is showing a cable run that's about 15 meters long, I should see in the middle nice and flat, and I will normally see a little bump here, and I will normally see a little bump here. And what this is showing me is my cable is roughly 15 meters long. That's where the large bump is. And right before the 15-meter mark, I have a little disturbance. And right before the 0 mark, I have a disturbance. Well, this is a termination maybe at the patch panel. And this over here is a termination maybe at the outlet jack. I expect a little bit here and I expect a little bit here, but if I start seeing a bunch of bumps and waves and so forth in the middle, I'm getting disturbances in my signal, disturbances in the force, disturbances in the signal that might be caused by sloppy terminations or other interferences along the way. So a TDR is taking advantage of these propagation delay skew, that sort of thing, and measuring that for me. We will do that later this semester on our cable run. One of the last things they mentioned is your marking of your twisted pair cabling. The outside jacket of my twisted pair cabling should clearly be marked by things like manufacturer, category, those sorts of things on my cable. And if I look at a twisted pair cable, I'm going to see something like this. Okay, every manufacturer does a little bit different, but I'm going to see stuff like this. And if I look at a sample cable label like this, as I go down through four PRs, 4 pair, 24 GA, 24 gauge, CMP, P for plenum. This is plenum rated cabling, showing me my category, so-and-so cable company, their part number, and then I see something out here, a footage mark. That's actually handy as I'm installing cable. I need to pay attention to the manufacturer, but as I'm pulling out of the box, I might be at the 500 foot mark. That's important because cable boxes come in 1,000 feet. So I know I'm about halfway through the box, but I can also pay attention to this number that if I start at 534, I pull my cable run and I end at 634, I just pulled 100 feet of cable. I know my cable runs 100 feet. So there's usually a footage mark on there that's handy for a couple reasons. So I pay attention to that. And again, I remind you about the general, riser, and plenum here too. Don't forget those. You should be able to identify those. And that's the majority of the stuff that we run into with twisted pair cabling. It's a lot, I know. But there's the majority of the characteristics and things that we run into twisted pair cabling. When we come back, we'll start in on our fiber optic.